Welcome to the AI Coach by Anil Nathu. Today, we're not just scratching the surface. We're diving headfirst into the really exhilarating world of vector databases. These aren't just another tech trend. Honestly, they are the unsung heroes, the intelligent powerhouses behind so much of the modern AI we interact with, every single day. Our mission: to transform your understanding of vector databases. We want to take you from foundational knowledge to a deep appreciation for the advanced tools, techniques, and technologies that make them truly intelligent. Think of this as your shortcut to being genuinely well-informed, ready to tackle the complexities, and, frankly, leverage the power of this rapidly evolving field. We're going to unpack how to make your vector database not just functional, but genuinely smarter, more efficient, and incredibly insightful. So what can you expect from this deep dive? Well, we'll start with the foundational concepts, definitely. Then we'll quickly escalate to advanced querying, performance optimization, some groundbreaking hardware innovations, and even explore cutting-edge hybrid approaches. Get ready for those aha moments, because we're going to illustrate precisely how these advancements deliver unbelievable speed, surgical accuracy, and a profound semantic understanding that will make your AI applications truly shine. Okay, let's unpack this then. What exactly are vector databases, and why have they become so, well, indispensable in our AI-driven world?
It really starts with a fundamental shift, a major shift in how you search for and, crucially, understand data. For decades, our digital world relied on a pretty rigid form of search, one that, well, often failed to grasp the nuances of human language and intent. Think about the limitations of traditional keyword search for a moment. Imagine you're trying to find that perfect vacation rental. You type in cozy mountain cabin, minimalist style. A traditional database, it just doesn't understand what cozy or mountain cabin or minimalist style actually mean beyond those literal words.
Right, it sees the words, but not the feeling or the concept behind them.
Exactly. It might show you cabins, sure, maybe even minimalist decor, but it won't understand the vibe you're going for. Similarly, if you're interacting with a chatbot and it needs those exact keyword matches to understand your maybe slightly complex question, you'll get frustrated pretty quickly. These are clear examples of the shortcomings of those strictly structured or exact match queries and simple keyword-based search. For you, the listener, this matters profoundly because, well, in an era of overwhelming information, you absolutely need systems that can grasp the intent behind your query, not just the literal words you type. The old way is like trying to understand a painting by only reading the labels on the colors. It misses the whole picture.
That makes perfect sense. Keywords are great for exact matches, no doubt, but they often fall short when we're dealing with the rich, messy world of human language and, well, conceptual understanding. So if keywords are the problem, how do vector databases step in to fill that massive gap and allow us to search by meaning?
This is where the magic truly begins to unfold. Vector databases are purpose-built to store, index, and query high-dimensional vector data. The core, really revolutionary idea is that these vectors represent the semantic meaning of unstructured data, whether that's text, images, audio, or even complex user behaviors. They enable speedy and accurate similarity searches, which are not just a nice-to-have, but an absolute essential for modern AI applications, like intelligent recommendation systems, sophisticated natural language processing, and advanced content retrieval.
Okay, vector embeddings. Semantic meaning.
Yeah.
But what exactly is a vector embedding? Can you break that down a bit?
Sure. Imagine taking a piece of text, an image, an audio clip, or even, say, a product description, and converting it into an array of numerical values, floating points, to be precise. This array, often with hundreds or even thousands of dimensions, it's not just a random string of numbers. No. It's a precise mathematical representation that captures the semantic meaning of that object within a learned vector space. To give you a concrete sense, think of an embedding as a numerical array, maybe with 384 dimensions.
Wow, 384 dimensions. That's hard to visualize.
It is. Don't let dimensions scare you, though. Think of it like a very, very detailed coordinate system. In 2D, you have X and Y. In 3D, you add Z. Now imagine adding hundreds or even thousands of these coordinates to describe every single nuance, every feature, every relationship, every underlying concept of a piece of text or an image or an audio clip. That's our high-dimensional space, a rich, multifaceted map where meaning actually lives. And this isn't just a random mapping, it's a semantic fingerprint where things with similar meanings get mapped to points that are close together in this complex multidimensional space. The closer two points are in this space, the more semantically similar their underlying concepts are. It's quite intuitive, actually, once you grasp the core idea.
That's a powerful image, a semantic fingerprint that captures the essence of anything. Can you give us an example that really illustrates how these vectors capture abstract relationships, not just surface-level words?
Absolutely. There's a kind of mind-blowing example from the early days of word-to-vec arithmetic that still resonates today. King, man plus woman, queen.
Wait, like actual math?
Actual math. It's not a joke. The vectors for king and man share attributes like royalty and male gender, right? When you subtract the man vector and add the woman vector, the model actually navigates through this semantic space and lands remarkably close to the vector for queen.
Yeah.
This simple equation, it just blew the AI world's mind because it unequivocally showed that vectors could capture these profound abstract relationships and allow for, well, arithmetic operations on meaning itself,
That is genuinely mind-blowing.
isn't it? And today, modern embedding models like sentence transformers, BERT, and OpenAI's text embedding models are far more sophisticated. They allow us to convert entire paragraphs, audio clips, images, product descriptions, you name it, into these powerful, dense vectors. And speaking of evolution, the real game changer here was the transformer architecture. This powers models like BERT, GPT, Palm, Gemini. This leap allowed systems to finally understand context across entire paragraphs, not just individual words or short phrases. This deep contextual understanding is what truly enables the rich, meaning-packed vectors we use today. We've moved beyond simple keyword associations to capture the full semantic depth of information.
That context-aware leap is truly incredible. So once we have these semantic fingerprints, these vectors floating around in their high-dimensional space, how do we actually measure their similarity? What metrics are key to this meaning-based search?
That's where distance metrics come in, and they are absolutely crucial. The key to meaning-based search is precisely measuring how close two vectors are in this high-dimensional space. Think of it like having a specialized ruler for meaning. These metrics are pivotal in everything from search engines to sophisticated recommendation systems. The real insight here for you, the listener, is understanding that each metric is like a different lens, offering a distinct perspective on what similarity actually means.
Different lenses. Okay, so what are some common ones?
One of the most common and widely used metrics is cosine similarity. Conceptually, it measures the cosine of the angle between two vectors. This means it focuses primarily on the direction of the vectors rather than their magnitude or length. The result is a value between -1 and 1, where 1 means they point in the exact same direction, highly similar, 0 means they're orthogonal, no similarity, and -1 means they point in opposite directions, highly dissimilar.
So it's about alignment, not necessarily size.
Exactly. It's crucial in information retrieval for ranking search results and in collaborative filtering for recommendations. Its strength is that it captures directional similarity, making it robust to varying data scales or lengths. For example, in text analysis, a short document on the same topic as a long document will still have a high cosine similarity because their semantic directions are aligned, even if their lengths, the word counts, are very different. It's kind of your vibe detector, telling you if two things are heading in the same semantic direction, regardless of how loud or long they are.
Okay, the vibe detector. I like that. What else?
Then we have Euclidean distance, also known as L2 distance. This is the one we all learned in school. The straight line distance, the most intuitive as the crow flies measurement, between 2 points in space. A smaller Euclidean distance indicates more similarity. Pretty straightforward. Unlike cosine similarity, though, it's very sensitive to magnitude. Longer vectors, which might represent more intense or prominent features, will naturally be further apart. So it's useful when those absolute distances between data points genuinely matter. It's more like a strict ruler, measuring absolute closeness, which is crucial when subtle differences in scale do matter.
Got it. Strict ruler versus vibe detector. And the last one.
And finally, the dot product. This is a scalar product of two vectors. You calculate it by multiplying corresponding components and summing the results. Interestingly, if the vectors are normalized, meaning scaled to a unit length, the dot product is actually equivalent to cosine similarity. It reflects both the alignment and magnitude of the vectors. It's often used in optimizing machine learning models, training neural networks, and in recommendation systems, partly because it can be computationally efficient. While it accounts for both alignment and magnitude, its effectiveness can be somewhat limited, particularly when we're dealing with the incredibly high dimensions these vectors often have. And that, funnily enough, brings us directly to one of the biggest hurdles this field faces. The infamous cursive dimensionality. That sounds less like a minor inconvenience and more like a significant challenge. Can you elaborate on why it's such a hurdle for traditional search methods when we're operating in these complex, high-dimensional spaces? Indeed, it's a profound challenge. It can absolutely cripple traditional search algorithms. with embeddings often reaching, 384, 768, 1 hour 24, or even 2048 dimensions. Our intuitive understanding of distance and proximity just breaks down. In these incredibly high-dimensional spaces, a strange phenomenon occurs where pretty much all points start to feel equally distant from each other.
Equally distant. How does that even work?
It's counterintuitive, I know. Imagine trying to find the closest person in a room with a billion dimensions. Everyone would seem roughly the same distance from everyone else. The space is just so vast. This makes it incredibly difficult to distinguish true nearest neighbors from points that are merely far away. And it renders brute force search checking every single vector against the query vector computationally expensive, if not completely impossible for large data sets. This curse explains precisely why specialized techniques are absolutely necessary for efficient and effective search in vector databases. Without these specialized methods, the immense power of vector embeddings would essentially be lost in the vastness and, well, the indistinguishability of their dimensions.
We've just navigated the dense forest of vector fundamentals and the looming shadow of the curse of dimensionality. It's clear that traditional methods simply don't cut it, but every challenge sparks innovation, right? So how do we outsmart this curse? How do we take these powerful but unwieldy vectors and make them truly intelligent, fast, and practical for real-world AI applications? This is where the engineering brilliance behind advanced querying techniques truly shines.
You're absolutely right. This is where we bring in the advanced techniques designed to dramatically improve data retrieval performance, speed, and accuracy. These directly impact a wide range of AI applications. The primary way we do this is through approximate nearest neighbor, or ANN, search.
Approximate, so not exact.
Exactly. The core idea behind ANN is a brilliant and highly practical trade-off. We accept a tiny bit of accuracy in exchange for dramatically faster search. For most AI applications, whether it's a recommendation system, a semantic search engine, or maybe a retrieval-augmented generation pipeline, getting close enough matches is perfectly sufficient. Think about it. When you're looking for a product recommendation, do you need the absolute single perfect match out of millions? Or is a highly relevant, top-tier suggestion good enough?
Yeah, usually the second one is fine, maybe even better if it gives some variety.
Right. Exactly. Nearest neighbor searches are often computationally prohibitive in these high-dimensional spaces. So ANN algorithms are critical for making these systems practical, efficient, and scalable enough to handle the demands of modern AI. It's the smart shortcut that gets us almost perfect results, but much, much faster.
So we're talking about smart shortcuts that get us almost perfect results much faster. What are some of the key ANN algorithms that make this possible, and how do they actually work under the hood?
There are several powerful algorithms, each with its unique approach to tackling the curse of dimensionality and speeding up search. First, we have HNSW, which stands for Hierarchical Navigable Small World.
Okay, that's a mouthful. Hierarchical, navigable.
It is, but imagine building a multi-level graph, like a series of interconnected maps. At the top level, you have a sparse map with long connections, letting you jump quickly across large distances in the vector space. As you go down the hierarchy, the maps become denser with shorter connections, allowing for more fine-grained navigation within local neighborhoods. Each vector point in the database connects to its nearest neighbors on multiple levels, and the search process involves basically walking this graph, jumping from node to node, efficiently moving towards the query point.
So it's like having an expressway system and local roads all layered together.
That's a great analogy. HNSW is known for being very fast and very accurate, making it ideal for real-time similarity search. Many popular vector databases like Weaviate, Milvus, Phase, and Vespa utilize HNSW because of its excellent performance profile. It's essentially a smart network that knows how to quickly navigate to the right neighborhood. The aha here is that we're accepting that tiny bit of imprecision to gain monumental speed, which for most AI applications is frankly a no-brainer.
Makes sense. What's next?
Next up is IVF, or Inverted File Index. This algorithm takes a different, maybe more intuitive approach. It first clusters vectors into groups, often using methods like k-means. Think of it like organizing a massive library into sections, fiction, nonfiction, sci-fi, history, and so on. When a query comes in, the system figures out which cluster or section of the library is most relevant, and then it only needs to search within those few relevant clusters rather than sifting through the entire collection.
So narrowing down the search space drastically from the start.
Precisely. This makes it much faster than brute force by allowing it to skip most of the data. IVF is great for large datasets and batch operations, and is frequently combined with product quantization for even greater efficiency.
Product quantization, you mentioned that. What's PQ?
Right, PQ or product quantization. This is primarily a compression technique, and it's incredibly clever. It works by decomposing the original high-dimensional vector space into multiple smaller, lower-dimensional subspaces. Each of these smaller subspaces is then quantized or compressed, effectively reducing the memory footprint needed to store the vectors.
So it shrinks the vectors down.
In a way, yes, it represents them much more compactly. This drastic reduction in storage requirements makes PQ incredibly useful in large-scale applications, especially when combined with IVF to form a hybrid index like IVF-PQ. For instance, Deep Lake, which is an open-source data lake for deep learning, uses an ANN algorithm based on PQ for rapid and accurate searches. This means you can store far more vectors in memory or on disk for the same cost, making massive datasets much more manageable.
Okay, HNSW, IVF, PQ. Any others we should know?
Another important algorithm is LSH, or locality-sensitive hashing. LSH works by taking high-dimensional data points and hashing similar points into the same bucket or cluster. It does this by creating multiple hash tables, with each hash function cleverly designed to maximize the probability that similar vectors will end up in the same bucket. When you have a query, you simply hash it using the same functions and check the contents of its corresponding buckets, drastically reducing the search space again.
So it's like sorting things into bins based on similarity.
Kind of, yes.
Yeah.
This makes it very efficient for extremely large data sets and well-suited for real-time applications where speed is critical, like large-scale image retrieval or recommendation systems. However, it's important to remember the trade-offs. LSH provides approximate results, and its accuracy depends heavily on the selection and number of those hash functions. It can also incur significant memory overhead for storing all those hash tables, and like other methods, it can still struggle with the curse of dimensionality if not carefully implemented.
Got it. Trade-offs everywhere.
Always. We should also briefly mention ANOI, which stands for Approximate Nearest Neighbors.
Oh, yeah.
Oh, yeah.
Seriously.
Seriously. It's another popular tree-based indexing algorithm designed specifically for approximate search. It builds a forest of random projection trees where each tree partitions the data differently, and then it searches these trees to find approximate nearest neighbors. It's known for having a pretty good balance of speed and memory usage, and it's particularly effective in scenarios like music recommendation systems.
That's a powerful toolkit for speeding up similarity searches. But what about queries that need to find not just a single closest match, but maybe a whole group of relevant items? Or what if you need a filter based on traditional data alongside the vectors? We're not just finding similar, we're finding similar and relevant to my specific criteria. That adds a whole new layer of precision, right?
Absolutely. This leads us to range queries, which are incredibly useful for situations where a precise threshold of similarity is more important than just getting the top K matches. Instead of just finding, say, the top 5 most similar items, range queries allow you to retrieve all items within a specified distance or similarity threshold from your query vector. This technique is crucial for applications that focus on finding an entire set of items that meet a minimum similarity requirement rather than just the single most similar one.
Can you give an example of where that's really useful?
Sure. Consider a compelling case study in drug discovery. Developers in the pharmaceutical industry can vectorize complex molecules, creating these functional representations tailored to specific purposes, like targeting certain disease pathways. Now, unlike conventional top K searches that might give you just a handful of the most similar candidates, a range search can identify all vectors, meaning all molecules, within a specified distance from the target molecule. This presents a much more comprehensive list of potential drug candidates that fall within a desired similarity range. That's indispensable for researchers exploring a broad set of options. This powerful feature also finds applicability in diverse domains like fraud detection and cybersecurity. Imagine identifying all potentially related transactions, say, all transactions within a certain semantic distance of a known fraudulent pattern. That's far more valuable than just finding the single absolute closest one. It prevents overlooking crucial, maybe slightly less obvious connections.
Okay, that makes a lot of sense, finding the whole neighborhood, not just the closest house.
Exactly. And to make our searches even more targeted and efficient, moving beyond just pure vector similarity, we can use techniques like multi-vector queries and scalar data filtering. Multi-vector queries allow you to use multiple query vectors simultaneously to find data that is similar to a combination of concepts, effectively allowing for more nuanced and complex searches, like finding something similar to both dog and fluffy. Scalar data filtering, on the other hand, is about combining the semantic power of vector search with the precision of traditional structured data filtering based on metadata.
So, like finding similar documents, but only those published after a certain date or tagged with a specific category.
Precisely. These directly impact accuracy by allowing us to combine semantic search with traditional data filtering based on specific attributes like dates, categories, authors, or keywords. For instance, you might search for relevant articles semantically, but simultaneously filter to exclude results from specific publications, or only include results within a certain price range, or tagged with a specific location. This achieves a much more precise and contextually relevant search result that pure vector search alone might not provide. It's about getting exactly what you need with no noise.
So, we know what these techniques are, and they sound incredibly powerful, but how do we ensure they run at peak performance without, breaking the bank? Because let's be honest, advanced AI can get expensive quickly if not managed well. This is precisely where AI coach by Anil Nathu can help you strategize, guiding you to make cost-effective, high-performance decisions.
You've hit on a critical point. Optimizing these advanced queries is absolutely crucial for achieving high performance and accuracy, especially when you're dealing with the massive volumes of high-dimensional data that characterize modern AI applications. Performance isn't just about speed. It's about making your systems economically viable and responsive enough for real-world use. One of the core aspects of this optimization is balancing speed versus accuracy. We touched on this with ANN. ANN algorithms inherently involve this trade-off. For many applications, exact nearest neighbor searches are just unnecessary. Accepting approximate results can significantly reduce query times, with often only a marginal, sometimes imperceptible impact on accuracy.
So, how do you decide where to draw the line?
The practical guidance here is to define different quality of service, or QoS, levels for your queries. For example, background tasks like nightly data processing or large-scale data deduplication might tolerate slower, more accurate searches, perhaps taking minutes or even hours. Who cares, right? It runs overnight. In contrast, user-facing queries such as those powering a real-time recommendation engine on an e-commerce site or a conversational AI chatbot need to prioritize blazing speed, often requiring millisecond response times, even if it means a tiny reduction in accuracy. Understanding your application's specific latency tolerance is absolutely key here.
That makes a lot of sense, tailoring the performance to the need rather than a one-size-fits-all approach. What about choosing the right algorithms themselves and making them perform optimally?
That's the next key step. Picking and tuning the right index. Vector databases should ideally support multiple indexes, HNSW, IVF, PQ, LSH, and others, to allow users to select the one that best suits their needs. It's definitely not a one-size-fits-all solution because different data sets and different query patterns benefit from different index structures. Once you've chosen your index type, the optimization process involves two main iterative steps. First, you tune its specific parameters, things like the number of layers in an HNSW graph or the number of clusters in an IVF index. Then you tune the search parameters, which dictate how the query actually traverses that index at runtime. This iterative tuning, combined with rigorous testing on your own data, is essential to get the most out of your chosen index for your particular dataset and application. You really shouldn't just rely on the defaults.
When we talk about performance, especially with intense computational demands like those of vector search, I immediately think of specialized hardware. How are GPUs changing the game for vector databases? This is definitely an area where AI Coach by Anil Nathu frequently advises clients, highlighting how smart hardware choices can lead to massive efficiency gains.
You're absolutely right to think of GPUs. Vector databases are known for their intense computational demands, primarily because vector operations involve a huge number of calculations that can be done in parallel, and GPUs are brilliant at parallel processing. Advancements in GPU technologies have led to really substantial performance improvements. Historically, GPUs were often perceived as prohibitively expensive for general vector search, but this perception is actually changing quite rapidly. Enhanced algorithms and more efficient ways to utilize GPU power are now making GPUs a viable and increasingly cost-effective option for low-latency, high-throughput vector search operations. The raw parallel processing power of a GPU can often crunch through vector comparisons orders of magnitude faster than a traditional CPU.
Orders of magnitude, so like 10x faster, 100x faster.
Potentially, yes, depending on the specific task and hardware. Consider a compelling case study from Zillis using their Milvus vector database with a GPU-based Kedro index. Their rigorous testing showed that this GPU setup achieved performance levels several to tens of times higher than a comparable CPU-based HNSW index, while only being 2 to 3 times more expensive.
Wow. So significantly faster for only moderately more cost.
Exactly. The clear lesson here is that GPUs are becoming an economically efficient option, providing significant performance advantages that, in many scenarios, far outweigh their marginal additional cost. Imagine getting 10x the performance for only 2x or 3x the cost. That's often a clear win for efficiency. Systems like NVIDIA's powerful framework and phase also actively support GPU acceleration, underscoring this pervasive trend across the industry.
So faster and increasingly cost-effective. Beyond computation, what about storage optimization? How do we keep costs down there, especially with the ever-growing size of these vector data sets?
Storage optimization is another crucial area for cost effectiveness, especially given the sheer scale of vector data we often deal with now. To minimize costs, data should ideally be stored in the most economical cloud object storage think services, like AWS S3 or Google Cloud Storage, and then retrieved on demand just for the queries that need it. This directly addresses the broader challenge of high storage requirements, often faced by vector databases. By decoupling storage from compute, you pay much less for inactive data. Furthermore, by carefully refining the scope of queries in advance, for example, by pre-filtering using metadata before you even perform a vector search, we can reduce the need for broad-scale data processing. This significantly enhances operational efficiency because you're only loading and processing the most relevant subset of data, saving both storage access costs and compute time. Smart filtering upfront saves resources down the line. Makes sense. Definitely. We also need to critically differentiate between computational efficiency for offline versus online use cases. These two scenarios have fundamentally different demands. Online applications, like real-time search or recommendations, typically handle small data volumes but at extremely high frequencies, and they demand stringent low-latency responses, often within milliseconds or seconds. Offline tasks, on the other hand, involve large-scale data processing, such as data deduplication, feature mining for model training, or large-batch data ingestion. Here, job duration can extend for minutes or hours, requiring high computational efficiency across massive batches of data rather than super low individual query latency.
So different optimization goals for different types of jobs.
Precisely. The solution here is often to enhance computational density. For example, leveraging specialized hardware like GPU indexing can significantly improve the handling of extensive data queries in those offline scenarios, churning through petabytes of data efficiently. This is particularly important for tasks involving vast data return in data mining applications, where retrieving substantial data volumes for large top-K searches poses significant bandwidth and algorithm efficiency issues. Developing efficient solutions to manage these large-scale retrievals, such as optimized data serialization, parallel processing frameworks, and smart data partitioning is crucial for robust and cost-effective offline vector database applications. It's about ensuring the right compute for the right job.
This is where we see vector databases truly integrate with the broader AI ecosystem, creating smarter, more intuitive applications that respond to user needs with uncanny intelligence. This is a core focus of AI Coach by Anil Nathu, helping organizations build these next-generation systems.
Absolutely. The future of intelligent data retrieval truly lies in combining the strengths of various techniques and integrating tightly with large language models, or LLMs. This synergy unlocks capabilities that neither technology could really achieve alone. A prime example of this is Retrieval-Augmented Generation, or AIR.
AIR-egg.
Yeah.
We hear that acronym everywhere now. What is it, really?
It's a process that significantly enhances internal search relevance and, critically, mitigates AI hallucinations by providing LLMs with retrieved, specific context from a reliable data source, like your vector database. Without AIR, LLMs often rely solely on their vast, but sometimes outdated or generalized, training data, which can lead to factual errors or those infamous hallucinations. AIR-RAG provides grounding. You can think of it as a pipeline. Retrieve relevant info, embed it, feed it to the LLM, generate a grounded response.
Okay, so how does that work in practice?
Imagine a company integrates all its internal documents, its knowledge bases, policy documents, product manuals, into vectors and stores them in a vector database. When an employee asks a complex question, an ANN query is performed against this internal vector database, retrieving the closest, most relevant data snippets. These highly relevant snippets are then passed to the LLM as part of the prompt, acting as factual grounding or context. The LLM then generates a human-like answer based specifically on the company's internal data, ensuring relevance, accuracy, and dramatically reducing the likelihood of generating incorrect or just made-up information. This is critical because LLMs, on their own, often struggle with grasping underlying intent and can yield irrelevant results or hallucinate. RAG provides that crucial semantic understanding and factual context to yield truly relevant and trustworthy results. It's indispensable for giving LLMs reliable memory and context.
So RAG helps ground LLMs in specific factual data, preventing them from making things up. That's a huge step forward for reliability. But what about the LLMs themselves actively helping the retrieval process, making the search itself smarter?
That's where LLM-aided retrieval comes in. Large language models, like advanced versions of GPT or BERT, can significantly enhance retrieval not just by generating text after retrieval, but by actively understanding context during the retrieval process. They can help generate better queries or even re-rank search results.
How would an LLM generate a better query?
Well, take contextual query expansion. If a user asks a vague question like, "Tell me about climate change," an LLM can understand the underlying intent and expand the query by adding related, more specific terms or phrases, like impact of climate change on polar ice caps, or latest research on renewable energy transition, leading to far more relevant results than the original broad query.
Ah, okay. It anticipates what you might really be looking for.
Exactly. Similarly, after an initial retrieval using maybe ANN search, LLMs can re-rank the results based on their deeper contextual and semantic understanding. They can discern which results are not just semantically similar, but also most relevant to the specific nuance of the user's intent, providing more refined and accurate final list. They can look at the retrieve chunks and say, okay, these three are really answering the question, these other two are just vaguely related. We've seen this in practice with research using LLMs like Google PaLM and Gemini alongside vector search tools like Face for enhanced web query retrieval. This demonstrated remarkable contextual understanding and prompting, with PaLM, for example, excelling at giving detailed tutorials when specifically instructed by prompts, showing how LLMs can directly improve the quality and relevance of information pulled from a vector database. It's like having an incredibly intelligent librarian who not only finds the books, but also helps you refine your question to find exactly the right paragraph within those books.
That's powerful LLMs not just generating, but actively improving the search itself. And what about combining different search strategies to get the best of all worlds? Because, as we've discussed, no single method is perfect for every scenario.
Precisely. This leads us to hybrid search techniques, which combine multiple strategies for enhanced search effectiveness. Imagine building a search system that combines, say, semantic similarity search for meaning with maybe traditional keyword search, like BM25 for exact term matches, perhaps adds maximum marginal relevance, or MMR, to ensure both relevance and diversity in results, avoiding redundant suggestions, and then maybe adds an LLM for final re-ranking to catch any subtle contextual cues. Tools like OpenSearch, for example, now offer robust hybrid search capabilities, showcasing its real-world adoption.
So you layer different strengths together.
Exactly. A key aspect of hybrid search is bridging sparse and dense vectors. Traditional dense vectors from models like BERT are excellent at capturing those subtle semantic nuances, the overall meaning. Think of them as painting a rich, detailed picture. However, they can sometimes struggle with brand new vocabulary, specific proper nouns, or highly specialized jargon not seen during training. On the other hand, sparse vectors, often generated by older but still highly effective keyword matching algorithms like BM25, are fantastic at precisely nailing those out-of-domain keywords or exact phrases. Think of sparse as the sharp, exact blueprint. Hybrid search intelligently combines the strengths of both, leading to enhanced search capabilities that offer both deep semantic understanding and precise keyword matching. It's also vital to combine this with metadata filtering, because pure vector similarity isn't always enough. You need context. Hybrid search leverages vector search plus metadata filtering using tags, dates, authors, categories, whatever structured data you have to ensure contextually relevant results, not just broadly semantically similar ones. This ensures you get results that mean what you're looking for and fit your specific criteria, like find documents similar to this concept, but only those written by this author in the last year.
So we're building a more complete picture, not just on what something means, but also its context. That's a huge leap. What about searching across different types of data entirely, like images and text, or even audio and video? Can we do that?
Absolutely. That brings us to cross-modal retrieval. This is really cutting-edge stuff. It involves retrieving results across entirely different data types, text, images, audio, video, by mapping them all into a unified embedding space. The key here is using multimodal AI models, which are trained on data sets containing multiple modalities simultaneously. These models learn to create embeddings where the representation of a concept is similar, regardless of whether it's expressed in text, seen in an image, or heard in an audio clip.
So the vector for a picture of a cat would be near the vector for the word cat.
Essentially, yes. A specific concept whether it's expressed in text, an image, or an audio clip, will map to a similar region in this unified embedding space. For example, imagine a user uploads an image of a famous landmark, say the Eiffel Tower, to a travel website. A cross-modal retrieval system would convert that image into a vector. Then, in that unified embedding space, it would be able to retrieve relevant text-based travel guides, blog posts, or tour listings that describe the Eiffel Tower, even though the original query was just an image. Or perhaps you could query with an audio clip of a bird call and retrieve images or text descriptions of that specific bird species. This capability unlocks incredibly intuitive and powerful search experiences that go far beyond what single-modality systems can achieve. It makes information retrieval feel almost magical in its understanding.
Privacy and distributed data are critical concerns in today's world, especially when dealing with sensitive information spread across different organizations or locations. What about making vector databases smart in a way that respects data sovereignty and keeps sensitive information secure without compromising search capabilities?
This leads us to a truly cutting-edge concept: federated vector similarity search. This is a significant and actively researched area, aiming to perform collaborative search across data silos while maintaining strict privacy. Researchers define vector data as a hybrid type in this context. It integrates both the high-dimensional embeddings, which capture the intrinsic features of an entity, and structured attributes, which provide additional context or metadata associated with that entity, like a user ID, a timestamp, or a category tag. This dual nature is crucial for enabling more precise and, importantly, private searches, as you can potentially filter based on metadata and semantic meaning without revealing everything.
So it's not just about the vector, but also the associated metadata, all while keeping privacy absolutely paramount. How does a framework like FedVS actually work to achieve that, especially in distributed environments where data providers definitely want to keep their raw data private?
The FedVS framework is a sophisticated two-phase process built on the foundation of trusted execution environments, or Ts, like Intel SGX.
Ts, what are those exactly?
Think of a T as a highly secure, isolated vault within a computer chip. Data and computations happening inside this vault are completely private and protected, even from the operating system or the administrators of the computer itself. This secure black box is absolutely essential for enabling private, distributed searches because it allows sensitive computations to occur without exposing the raw data to untrusted parties, including the central server orchestrating the search.
Okay, a secure vault on the chip. So how does FedVS use it?
In Phase 1, deriving a threshold for nearest distance, the individual data providers, think of them as separate companies or departments, each holding their own sensitive data, perform a local search on their own data first. They then discretize their potential candidates into anonymized intervals of distance without revealing the actual data points or their precise distances. It's like saying, I have 5 candidates in the very close bucket, 10 in the medium close bucket, etc. Crucially, a central server, operating within its own T, then calculates an optimal global distance threshold using a binary search based only on these anonymized intervals provided by all participants. The key here is that the central server calculates this threshold without ever seeing the raw data or the exact distances from any of the providers. Sensitive distances are never exposed directly, only their relative positions within broad, anonymized buckets.
Clever. So it finds a global cutoff without seeing the details. What happens in Phase 2?
Then comes Phase 2, selecting top K from refined candidates. In this phase, each data provider takes the global threshold determined in Phase 1 and uses it to eliminate any local candidates whose distance is larger than that threshold. They essentially filter their local results based on the global standard. Only the potentially relevant, privacy-preserving candidates that meet the threshold are then sent, often still in an encrypted or protected form, to the central server's T. The central server, still operating securely within its T, performs the final top K selection for these filtered candidates submitted by all providers using something called an oblivious priority queue. This basically means it can rank and select the top candidates without ever actually seeing the sensitive distance values themselves, only their relative order. It's like sorting a deck of cards without knowing the numbers, only whether one card is higher or lower than another. This entire two-phase approach ensures that the similarity search can happen across distributed private data sets while maintaining strict data sovereignty and privacy guarantees.
That's incredibly clever, especially the use of Ts and these oblivious techniques to protect the actual data during sensitive operations. But such a complex system could potentially be slow or communication heavy. What kind of optimizations are built into FedVS to make it even more efficient, particularly regarding communication costs?
That's a very practical concern, and the researchers have indeed incorporated several clever optimizations for FedVS to ensure it's not just secure, but also practical and efficient. To reduce communication costs, for example, in Phase I, instead of sending full distance intervals, they use a simplified representation, communicating only the right endpoint of the interval. This significantly cuts down on the amount of data transferred. They also explored replacing the traditional binary search for the threshold, which might require many back-and-forth rounds, with a min-heat-based search. This bounds the number of candidate distance values needed, further reducing data transfer between providers and the central server.
Okay, less data flying around. What else?
Another key optimization is pruning via contribution estimation. The motivation here is to avoid the inefficient scenario where you might select, say, the top K candidates from every single data provider, even if some providers have data that's clearly irrelevant to the query.
Right, why bother sending candidates, won't make the final cut?
Exactly. To eliminate these likely redundant local candidates early, FedVS uses two primary factors: the estimated distance of a provider's best candidates to the query vector, and the selectivity of any attribute filters applied, meaning how many local candidates pass the basic metadata filter. To achieve this efficiently, each data provider first builds a cluster-based learned index, or CLI, offline. You can think of a CLI as a local pre-computed map of where its data clusters are, allowing you to quickly estimate the density and relevance of data points within certain regions of the vector space. Then, online, when a query comes in, each provider uses its CLI to estimate the distance of its potentially k-called nearest neighbor, adjusted for filter selectivity, as its own contribution. If this estimated contribution is too far off, it can prune away many local candidates without even needing to fully evaluate them. This intelligent local pruning mechanism ensures that only the most promising candidates are considered for global aggregation, significantly enhancing efficiency by not sending unnecessary data across the network.
Those optimizations sound like they'd make a huge difference in real-world performance. What were the actual performance benefits observed in experiments, showing how FedVS stands out?
The performance benefits of FedVS reported were quite impressive and speak volumes about its innovation. In experiments where it was rigorously compared against other federated search algorithms, FedVS consistently demonstrated superior overall efficiency. It achieved, at most, 27.25x lower search time and 15.32x lower communication cost.
Wow, that's a massive difference.
It really is. This means searches are dramatically faster, completing in a fraction of the time, and require far less data transfer, which is a huge win for distributed systems, especially where network bandwidth is limited or costly. Furthermore, FedVS consistently achieved the highest recall, up to 32.03% higher than the other algorithms it was compared against. This means it found significantly more of the truly relevant results hidden across the distributed dataset, all without compromising privacy. The framework also showed remarkable robustness and scalability, maintaining its superior performance even as the number of query results requested, or the number of participating data providers, BEM. This indicates that FedVS is a highly effective, robust, and practical solution for federated vector similarity search with strong privacy guarantees, really pushing the boundaries of what's possible in secure, distributed AI.
We've covered a lot of highly technical ground today, delving into the mechanics and optimizations of making vector databases smarter. So, what does this all mean for real-world applications? How are these smarter vector databases changing industries right now? And how can AI coached by Anil Nathu help you harness these changes? This is where we truly connect theory to practical impact.
Indeed. The advanced capabilities we've discussed are rapidly being deployed across numerous sectors, revolutionizing how we interact with information and making AI systems far more powerful, intuitive, and efficient in tangible ways. Let's start with recommendation systems. This is a classic application where vector databases truly shine, powering everything from what movies you watch on streaming services to what products you see on e-commerce sites. The core functionality is to represent items, like movies, songs, products, and users as vectors, where similar items and users are located closer to each other in this multi-dimensional meaning space.
So my vector should be close to the vectors of things I like.
Exactly. The process involves embedding items and users, perhaps based on their features, genres, descriptions, or past interactions, then learning these embeddings via machine learning algorithms like matrix factorization or deep learning. Once you have these vectors, you calculate similarities using metrics like cosine similarity. And finally, you generate recommendations based on vector proximity. If a user's vector is close to a movie's vector, it's likely a good recommendation. The benefits are profound. Vastly improved personalization, offering truly tailored suggestions. diversity in recommendations, helping break users out of filter bubbles, effective cold start problem mitigation, allowing new items or users with minimal history to still receive relevant suggestions, scalability to handle massive catalogs and user bases, and constant learning as user preferences evolve over time. You can build practical systems for movie recommendations using tools like sentence transformers and nearest neighbors, even adding things like Levenstein distance for correcting user typos in search queries. Or build food or job recommendation systems using tools like ChromaDB and Hugging Face models. These are becoming very accessible.
That's incredibly practical. Moving from recommendations, how are vector databases changing how we search for information generally, moving beyond that simple keyword model we started with?
They're fundamentally redefining semantic search engines. Unlike traditional keyword-based search that only looks for exact word matches, semantic search goes way beyond keywords. It converts text into these high-dimensional vectors that capture the semantic essence, the underlying meaning of the content. This allows search engines to return results that are semantically similar to the query, even if they don't contain the exact keywords. And so there's a fantastic demo using Python, sentence transformers, and ChromaDB. Imagine querying, find something about domestic animals. A traditional search engine might struggle if the documents don't use that exact phrase. But a semantic search engine wouldn't just look for those words. It would understand the concept of domestic animals and intelligently return results like dogs are loyal companions, cats are playful and curious animals, and maybe kittens love chasing things and exploring even though the exact word domestic isn't present in those sentences.
That really is the magic of semantic search. It understands your intent.
It does. And this semantic enrichment also extends to structured data in what are sometimes called distributional relational databases. These are essentially word vector databases that use these distributional vector representations to enrich the semantics of structured data. Imagine having a traditional relational database, like a spreadsheet of products with columns for category, color, material, but then infusing every text field, maybe even the category names, with its semantic vector. This type of database offers several compelling advantages. It supports schema-agnostic databases, meaning users can potentially query data without needing to know its exact structure beforehand. It enables true semantic search across both structured and unstructured fields. It helps with schema integration across disparate data sources, and it can even facilitate certain kinds of inductive and abductive reasoning. The crucial point here is that these semantic associations are automatically captured from corpora, learned from vast amounts of text data, in contrast to the labor-intensive and often brittle process of manually curating ontologies and rule-based knowledge bases. The system naturally understands relationships without being explicitly programmed for every single nuance.
It's clear that understanding meaning, not just words, is a game changer. How is real-time vector search making an immediate, tangible impact across various industries today, beyond just general search or recommendations?
Real-time vector search is truly a game changer across industries, providing immediate insights and enabling rapid decision-making in critical situations. In financial services, for example, it's revolutionizing fraud detection and risk assessment. Financial institutions are encoding vast amounts of transaction data, customer profiles, and behavioral patterns as vectors. Real-time vector search allows them to rapidly match incoming transactions against known patterns of fraudulent behavior, enabling instant identification of suspicious activities, sometimes even before a transaction fully clears, and leading to much quicker response times, drastically reducing potential financial losses. For risk assessment, models can leverage real-time vector embeddings to provide up-to-the-moment evaluations of market conditions, counterparty risks, and portfolio exposures, optimizing investment decisions with unparalleled agility.
So catching fraud almost instantly. What about other areas?
In logistics and supply chain management, coupling generative AI with real-time sensor readings from vehicles, containers, and warehouses allows for continuous analysis in dynamic conditions. By vectorizing sensor data, like temperature, location, vibration, and combining it with contextual information, like traffic, weather, systems can optimize route planning, reduce delivery times, minimize spoilage, and lower inventory holding costs. Imagine a truck carrying perishable goods hits unexpected traffic. The system can instantly identify an alternative route, predict the potential impact on spoilage based on temperature vectors, and even alert distribution centers downstream, all in real time. It doesn't just streamline operations, it gives organizations the agility to respond quickly to unforeseen disruptions.
That's amazing, real-time optimization based on sensor vectors.
And even in defense and intelligence, real-time vector search holds immense potential for threat hunting and intelligence analysis. Vector embeddings can represent complex features like radar signatures, satellite imagery patterns, communication patterns, or even cyber attack signatures. Real-time systems can swiftly compare incoming data streams to a comprehensive database of known threats, anomalies, and historical intelligence. This enables military and security personnel to rapidly identify potential threats, such as a new type of aerial vehicle, suspicious troop movements indicated by patterns in imagery vectors, or novel cyber attack vectors, allowing for informed decisions with unprecedented speed.
Those are incredibly impactful real-world applications that truly illustrate the smarter aspect. Now, a while back, we touched on RAG and its limitations, particularly when dealing with intricate relationships. How are graphs being integrated to make RAG even smarter, especially when handling complex multi-hop reasoning?
That's where integrating with graph databases, specifically a concept often called graph RAG, comes into play. The core idea is that vectors and graphs are better together. Graph RAG directly addresses a key limitation of standard RAG, which often struggles with intricate multi-hop relationships between pieces of information. While vector similarity is excellent for finding semantically similar chunks of text, it doesn't inherently understand the connections between entities mentioned in those chunks.
So vectors find similar stuff, graphs understand how the stuff is connected.
That's a great way to put it. By representing knowledge as a graph structure, nodes representing entities, people, places, concepts, and edges representing their relationships, GraphRag can truly enhance the AI's ability to reason, navigate these relationships, and retrieve information that requires more than just a direct semantic match. How it works is quite comprehensive. GraphRag can capture entities and their explicit relationships within a knowledge graph. This enables true multi-hop reasoning by allowing the LLM to follow chains of connections in the graph. Who managed the person who wrote this document? This provides more contextually relevant results. It effectively combines both structured data from the graph and unstructured data from vector embeddings, and can even significantly improve the explainability of LLM outputs by making the reasoning process more traceable to the graph's connections. The key components of such a system typically involve a document database for raw text, a vector database for embeddings, a graph database for entities' relations extracted from the text or metadata, and finally, an LLM coordinating it all. Raw data is processed into both the VDB for semantic search and the GDB for its structural relationships.
Can you give an example of that in action?
Sure, there's a compelling Supreme Court case demo. Imagine a complex legal data set involving numerous cases, judges, precedents, legal arguments, lots of interconnected pieces. A simple vector search might find relevant documents based on semantic similarity. But with GraphRag, the semantic search from the VDB can first act as a filter on the graph in the GDB, focusing the graph traversal on relevant nodes and edges, perhaps identifying all cases related to a specific constitutional amendment that were heard by a particular set of judges. The LLM then leverages this graph-informed perspective to generate more precise, contextually grounded queries against the filtered graph, allowing for a deeper exploration of complex legal data than either system could achieve alone. This synergy allows the LLM to ask more nuanced questions, like what precedents were cited in cases related to Amendment X decided by Judge Y, leading to much richer, more accurate, and verifiable insights by actually traversing the relationships in the legal knowledge graph.
This has been an incredible deep dive into making vector databases smarter and more intelligent. From fundamental concepts to cutting-edge privacy frameworks and hybrid approaches, we've seen the immense potential. But with great power comes responsibility and also practical considerations. What are the common pitfalls and what are the best practices you need to keep in mind for anyone building solutions with AI Coach by Anil Nathu?
You're absolutely right. Effective implementation requires careful planning and a strategic approach to maximize efficiency and reliability and avoid some common headaches. There are several significant challenges that must be acknowledged and addressed head-on. First, there's the sheer massive data scale. Storing and indexing literally billions or even trillions of vectors efficiently is a primary challenge, especially for applications involving large language models and vast corporate or web data sets. Closely related is the computational cost. Vector similarity searches, especially exact ones, are inherently computationally intensive operations, requiring highly optimized algorithms like ANN and often powerful hardware to mitigate this burden.
Scale and cost, the usual suspects. What else?
Then there's the issue of dynamic data. In today's rapidly evolving AI landscape, models get updated, underlying source data changes constantly. Maintaining data freshness and consistency in the vector database creates significant challenges for efficient updates and minimizing system downtime or stale results. Storage requirements also balloon as the size of LLMs and the corresponding vector databases increase, leading to higher demands for memory and disk space, which translates to cost. We also face data complexity. Converting diverse data types, raw text, varying image formats, different audio codecs into consistent, comparable vector forms requires specialized techniques. Robust feature extraction, high-quality embedding models, sophisticated signal processing, often followed by normalization. It's not always trivial.
Getting everything into the right vector format consistently.
Exactly.
Mm-hmm.
And finally, integration poses its own set of challenges. Bridging the gap between different vector representations, e.g., word embeddings versus sentence embeddings versus image embeddings, with diverse LLMs, and aligning their semantic understanding across complex multi-stage pipelines is a complex engineering task. And of course, the curse of dimensionality we discussed earlier remains an underlying challenge, even with ANN algorithms, requiring careful management to avoid performance degradation as dimensions grow.
Those are indeed significant hurdles that highlight the need for expertise. So what are the best practices to navigate these challenges and ensure a successful, intelligent implementation?
Drawing from various experts and resources, here are some battle-tested best practices that are crucial for success. First, understand your data requirements thoroughly. Before you even think about choosing a database, clearly define your data's type, its volume, its inherent complexity, and critically, the frequency with which it will be updated. This foundational step will guide all your subsequent technical and architectural decisions. Second, choose the right vector database for your specific needs. The market offers a rich ecosystem, each with unique strengths. Is it managed or self-hosted, open source or closed, optimized for scale or ease of use?
Yeah, options like Pinecone, Chroma, Waviate, Milvus, Qdrant, QdVector, Deep Lake, Face. It's a lot to consider.
It is. Evaluate them based on your scalability needs, performance targets, indexing capabilities, which ANN algorithms do they support, storage options, integration ease, and community support. Third, optimize hardware and software. Select hardware, maybe powerful GPUs if the workload warrants it, and software configurations that are specifically optimized for vector processing. If you're in the cloud, look at providers offering specialized GPU instances or vector-optimized compute options. Fourth, focus on scalability from day one. Design your database architecture and select scalable hardware or cloud services to handle anticipated increases in data volumes and query loads. Distributed vector databases are designed precisely for this kind of horizontal scaling. Fifth, and this is crucial, ensure robust data security. Implement measures such as fine-grained access controls, comprehensive data encryption, both at rest and in transit, and regular monitoring for unusual activities. This is especially critical with potentially sensitive AI data.
Okay, understand data, choose wisely, optimize hardware, plan for scale, lock it down. What else?
Sixth, use the right similarity metric consistently. Make sure you're not accidentally mixing cosine similarity with Euclidean distance in the same application context without a very good reason, and always normalize your vectors if required by your chosen metric. Seventh, keep embeddings consistent. Avoid combining outputs from different embedding models in the same index without careful handling or re-embedding, as they likely represent meanings in different incompatible semantic spaces, leading to nonsensical results. Eighth, tune index parameters meticulously. Don't blindly rely on default settings. They're almost never optimal for your specific data distribution and performance needs. Test and tune parameters like fconstruction or M and HNSW. Ninth, manage memory carefully. For very large datasets or extremely high-dimensional vectors, consider advanced compression techniques like BQ or intelligent data partitioning to avoid running out of memory during indexing or querying. 10th, handle real-time updates properly. If your data changes frequently, use vector databases that offer native support for efficient live updates, deletions, and insertions, like Pinecone or Qdrant, to prevent the performance degradation that can come from constantly rebuilding static indexes. 11th, combine metadata filtering with semantic search. Leverage hybrid search capabilities to avoid contextually irrelevant results that pure semantic similarity might sometimes produce. Ensure both semantic relevance and factual or contextual accuracy. Finally, and perhaps most importantly, evaluate, monitor, and iterate continuously. Lack of observability is a killer. It can lead to undetected issues like degrading accuracy over time or silently overloaded indexes. Log and monitor everything: recall, precision, latency, resource usage to maintain peak performance and relevance. And maybe a pro tip: hybrid systems combining various strengths like vector search plus keyword search plus filtering often work best for tackling complex real-world problems. Don't be afraid to mix and match.
This deep dive has shown us the immense potential and complexity of intelligent vector databases, from foundational principles to cutting-edge optimizations and real-world impact. Now, for your actionable takeaways straight from AI Coach by Anil Mathu.
Okay, let's boil this down. Here's a practical action plan, a roadmap to help you implement the key learnings from today's discussion and truly enhance your own AI projects. First, assess your data and needs. Seriously, this is your foundational step. Clearly define the type, volume, complexity, and update frequency of your data. Determine if your application needs that real-time, low-latency processing for user interactions, or if it can tolerate slower batch operations for things like nightly analytics. These insights guide everything else. Second, explore advanced indexing techniques. Don't just pick the default. Research and actively experiment with approximate nearest neighbor, or ANN, algorithms like HNSW, IVF, PQ, maybe even LSH depending on your scale. Understand the critical trade-offs between search speed and accuracy for your specific use cases. And don't forget to meticulously tune those index parameters through rigorous testing. Small tweaks can yield big gains. Third, investigate hybrid approaches. Think beyond pure vectors. Consider combining vector search with traditional metadata filtering for more contextually relevant and precise results.
Explore hybrid search techniques that blend sparse, keyword, and dense semantic vector methods, giving you the best of both worlds. And for truly complex relational data, look into integrating with graph databases to unlock that powerful multi-hop reasoning capability. Fourth, leverage LLM integration strategically. Plan for Retrieval-Augmented Generation, or RAG, pipelines. This will significantly enhance your large language model applications by providing specific relevant context retrieved from your vector database, mitigating hallucinations and boosting factual accuracy. Also, experiment with LLM-aided query expansion and re-ranking for improved overall search outcomes, letting the LLM intelligently refine and prioritize results. Fifth, optimize for performance, including hardware. Evaluate the potential benefits of GPU acceleration for your computationally intensive tasks, especially if you're working with large-scale operations or require ultra-low latency. Implement quality of service, or QoS, levels to strategically balance speed and accuracy across different types of queries your system handles, ensuring critical user-facing functions are always snappy. Sixth, prioritize scalability and reliability from the start. Choose vector databases or architectures that inherently support scalability, often through distributed designs, allowing you to grow seamlessly with your data. Critically, implement robust monitoring and logging practices across your entire vector search system. You need to ensure long-term stability and proactively identify issues like degrading accuracy or overloaded indexes before they impact users. And finally, number 7, embrace continuous learning. This field is moving incredibly fast. The landscape of vector databases, embedding models, and AI integration techniques is rapidly evolving. New algorithms and approaches emerge constantly. Foster a culture of experimentation and ongoing learning within your team. Stay curious, read papers, try new tools. That's how you stay ahead of the curve and keep your AI applications at the cutting edge.
And that wraps up our deep dive into making your vector database smarter and more intelligent. Wow. What stands out to you from today's conversation? We've covered such a huge range, haven't we? From the fundamentals of vector embeddings and that tricky cursive dimensionality to really cutting-edge techniques like FedVS for privacy-preserving search and GraphRag for complex reasoning. It's amazing how each advancement makes AI systems more capable and nuanced.
It really is. This journey into advanced vector database intelligence truly highlights that knowledge is most valuable when it's understood and actually applied. The synergy we talked about between optimized queries, these hardware innovations like GPUs, and thoughtful AI integration with LLMs and graphs, it isn't just theoretical anymore. It is fundamentally transforming possibilities across pretty much every industry imaginable.
Indeed. That ability to search by meaning, not just matching words, is such a profound game changer. We see it everywhere, from personalized recommendations that finally get you to real-time fraud detection systems that catch anomalies in milliseconds. We sincerely hope this deep dive with AI Coach by Anil Nathu has given you the insights and, perhaps more importantly, the confidence to go out and build truly intelligent, robust, and impactful AI systems. Thank you for joining us today. Visit the AI Coach website for more AI insights.